So we are looking today at doing some review problems out of the end of chapter 2. And in particular, we're focusing on two concepts overall. We're focusing on the mole concept. So those are all those conversions that we did in Monday's lecture. Grams to moles, moles to particles, particles to moles, all that stuff. And then also the empirical formula stuff that we did at the end of Wednesday's lecture. So we're going to try to get a little piece of both here. All right, one of the most common problems that got thrown my way as a result of the post-lecture activity was I didn't know how to do that ions question in SmartWork. Well, here we have an example of a similar kind of question. How many calcium ions are in 0.955 moles of calcium phosphate? So what we have to do here is we got to get ourselves organized so that we do the correct conversions in the correct order. So we have currently moles of calcium phosphate. This is the information that was given to us. Now, there are two ways that we can go about solving this problem, and they both are pretty much the same, just in different orders. We can turn this moles of calcium phosphate into moles of calcium just by using that chemical formula. And then once we have the moles of calcium, turn that into ions of calcium using Avogadro's number. The alternative pathway is that we could instead turn the moles of calcium phosphate into formula units of calcium phosphate using Avogadro's number, and then turn those formula units into ions using the chemical formula. Either way we did it, we would end up with the exact same result. It's just a matter of what order you feel most comfortable going with. So let's take the purple path here because I think that one's the most direct in terms of looking at this going from moles to particles to parts of particles. So if we start with our 0.955 moles of calcium phosphate, we want to go from moles to formula units. So we're going from moles, big picture, to particles, formula units, small picture. Whenever we're going from something to particles, we know that Avogadro's number is going to be involved. Avogadro's number goes here with the formula units, 6.022 times 10 to the 23rd. There are Avogadro's number of formula units in 1 mole of the substance. So my moles cancel. I'm left with formula units. So if I was just asked for how many calcium phosphate particles there are, this is as far as I would need to go. But I'm asked one more question here. I'm asked how many ions there are. And now I need to look at the chemical formula itself. Because the chemical formula says that for every calcium phosphate, there are 3 calcium ions. Comes directly from the chemical formula itself. So one of the things with these kinds of problems is there are a lot of directions that we can go once we have the particle itself. We could ask you the number of calcium ions, like we are here. We could ask you for the number of phosphate ions, in which case that would just be a 2-to-1 ratio instead of a 3-to-1 ratio, because there are 2 phosphates in the molecule. We could ask you for the number of phosphorus atoms, which would also be 2-to-1. We could ask you for the number of oxygen atoms, which in that case would be 8-to-1, because we're taking the 2 subscript multiplied by the 4 subscript to give us 8 overall. But for the calcium, 0.955 multiplied by Avogadro's number, multiplied by 3 significant figures because of the 3 here in our initial measurement, we get 1.73 times 10 to the 24th calcium ions. So the real key, the trick to this particular problem was in its kind of ordering. We had to make sure that we took care of all of the steps. So we had to go from big picture to small picture, which meant Avogadro's number had to be involved. And then we had to break down that formula unit into individual pieces. That's where that 3-to-1 ratio comes in. Now, if you had done the blue path would have been identical. Only difference would be that those 2 conversions would have been flip-flopped. You would have gone, there are 3 moles of calcium in every 1 mole of calcium phosphate, again, going by the formula. And then every mole of phosphor, every mole of calcium has Avogadro's number of ions in it. The math would have been exactly the same. We would just kind of rearranged our order. Any questions about this particular example? Right then, let's move on. How many grams are in 1.48 times 10 to the 22nd formula units of cadmium 2 nitrate? All right, so this is another type of conversion problem. Can give you a little bit of issue if you're not careful. But again, the first thing that you should do is sketch out your plan. Sketch out what steps that you need to do the calculation itself. So we're starting with formula units of cadmium nitrate. And we're asked to go to grams. So again, we're going from the very, very, very small world of particles to the big world of grams. Now, there's no direct conversion between formula units and grams, But there's an indirect conversion if I turn those formula units into moles and then turn those moles into grams using the molar mass of cadmium nitrate. And so that's the process that we're going to undertake here. We know to go from formula units to moles, we're going to have to use Avogadro's number. Again, Avogadro's number is the thing that bridges us between particles and moles. So if I'm starting with a small something and I'm turning it into a bigger something, I've got to use Avogadro's number. So starting with 1.48 times 10 to the 22nd formula units of cadmium nitrate. My first step is to convert those formula units into moles. The conversion there is 1 mole for Avogadro's number of formula units. So my formula units cancel out. Now I have moles of cadmium nitrate. I need to turn them into grams. For that, I need the molar mass. Molar mass of cadmium is going to be 1 cadmium plus 2 nitrogens and 6 oxygens. Remember, the subscript of 2 there gets distributed over every element inside the parentheses. So I need 2 nitrogens and 6 oxygens as a result. Cadmium, element number 48, is 112.41. Nitrogen, element number 7, is 14.01, and there are 2 of them. Oxygen, number 8, is 16 grams per mole, and there are 6 of them. Molar mass, 236.43 grams in 1 mole. Now my moles have canceled. So I do out the calculation, again, multiply by everything up top, divide by everything in the bottom, 1.48 times 10 to the 22nd, multiplied by 236.43, divided by Avogadro's number, 6.022 times 10 to the 23rd, to 3 significant figures, we get 5.81 grams of cadmium nitrate. So the most important tip I can give you with these kinds of problems is organization. Figure out where you are, where you need to go, and try to link them together using those conversions that we have. And the conversions that we have fall into one of 3 categories. it's either Avogadro's number, we're going from particles to moles or moles to particles, molar mass, going from grams to moles or moles to grams, and the chemical formula itself, if we're converting between compounds and elements or ions. Those are the three types of conversions that we can use in this kind of problem. It doesn't get any more complicated than any of those. Just a matter of figuring out which one that you need and making sure that you set it up correctly so that you can see and cancel out the units as you're going through it. Any questions with this example? All right, so here's your first problem of the day. What mass of aluminum oxide in grams contains 1.88 times 10 to the 21st atoms of aluminum? All right, no real time limit on this one. Take what time you need. Get yourself organized and make sure that you're following all the steps that you can. You'll walk around and try to help you out, troubleshoot as we go. So, like I said before, this has two divergent paths. You can take the blue path or the purple path. Either one is perfectly fine, perfectly acceptable. I'm going to take the blue path this time. So I start with my 1.88 times 10 to the 21st atoms of aluminum. On the blue path, I'm going to convert that to moles. So go straight into Avogadro's number, 6.022 times 10 to the 23rd atoms in 1 mole. Now, most of you I saw as I was looking around had this step in there somewhere. Now, some of you misinterpreted it and multiplied when you should have divided. This is where that dimensional analysis technique helps, because you can see clearly that by dividing, the atoms cancel. Whereas if you just throw out numbers there, you don't necessarily connect all the dots the way that you should. Second step, there are 2 moles of aluminum in every 1 mole of aluminum oxide. Again, this is where that dimensional analysis helps. If you just multiplied by 2 because you saw that there were 2 aluminums in there, you missed the point. That's where the unit cancellation kind of helps. And then finally, aluminum oxide. Aluminum is 26.98 times 2. Oxygen is 16. There are 3 of them. Total mass is 101.96 grams. So if I do all the calculating, 1.88 times 10 to the 21st, multiplied by 101.96, divided by Avogadro's number divided by 2 to 3 significant figures, I get 0.159 grams of aluminum oxide. And that should be, that should be the correct answer. So again, if you came in close, so if you're in this range here, you got 3 times or 0.3 instead of 0.159. That's because you forgot that 2-to-1 ratio. You forgot this middle step between aluminum and aluminum oxide. If you got one of these large exponential numbers like this one, that's what I was talking about. That's that scientific notation mistake that you made when you punched the numbers into your calculator. All right, any questions with this example? All right, let's move on then into empirical formulas. And so I've got one problem that I'm going to do. I'm going to turn around and give you one problem to practice on, and then we're going to call it a day. This one's pretty straightforward. Organic acid is composed of 26.1% carbon, 4.38% hydrogen, 69.52% oxygen by mass. What is the empirical formula? So remember our steps here. First thing, turn all the percents into grams just by changing the unit. 26.1 grams of carbon, 4.38 grams of hydrogen, 69.52 grams of oxygen. Step 2, turn all of these grams into moles by dividing by their molar masses. 12.01 grams of carbon in 1 mole of carbon, 1.01 grams of hydrogen for 1 mole of hydrogen, 16.00 grams of oxygen in 1 mole of oxygen. So I do all the calculations. 26.1 divided by 12.01 to 3 sig figs, I get 2.17 moles of carbon. 4.38 divided by 1.01, I get 3 sig figs, 4.34 moles of hydrogen. 69.52 divided by 16, I get 4.35 moles of oxygen. So unlike some of the problems that we did on Wednesday, this one looks pretty straightforward if you can do a little bit of mental math. We already can see that the hydrogen and oxygen are essentially the same. And they look not that far off from the carbon. Now, just to be sure, let's divide by the smallest number and see if we get whole numbers when we do. So dividing each one by 2.17, I get 1 carbon. 4.34 divided by 2.17 is 2. So we get 2 hydrogens. 4.35 divided by 2.17 is 2.00, so 2 oxygens as well. All the numbers came out as whole numbers this time, so I don't have to do any of that fractioning multiplying stuff. The empirical formula is just this ratio: carbon, 2 hydrogens, 2 oxygens. This happens to be the empirical and molecular formula for formic acid, which is the simplest of the organic acids. Not that you need to know that, it's just, common trivia that you want to impress everybody that you know with. All right, any questions with this example? All right, so our remaining time is going to be with this problem. There's a couple of dimensions to it. We are told that phosphorus burns in pure oxygen with a bright white light. The product of the reaction is 43.64% phosphorus, 56.36% oxygen. Has a molar mass of 284. Now you have to fill in 2 blanks here. The first blank, I want the empirical formula. Second blank, I want the molecular formula. Don't worry about formatting. Just punch in the element and the number of atoms that go with that element. So we have phosphorus and oxygen in a reaction to make a compound. And we're given its mass percent data, we're given its molar mass data. We need to find the empirical and molecular formulas. So again, we start with the same kind of process that we have all along. Turn the percents into grams. So 43.64 grams of phosphorus and 56.36 grams of oxygen. And now we're going to turn that into moles. So 30.97 grams of phosphorus in 1 mole of phosphorus, 16.00 grams of oxygen in 1 mole of oxygen. My grams of phosphorus cancel out, and 43.64 divided by 30.97 is 1.409 moles of phosphorus. 56.36 divided by 16 gives me 3.523 moles of oxygen. All right, so unlike the previous problem, this one is not nearly as clear cut. I can't just tell by looking at it what the ratios are. So I'm going to definitely want to divide here both numbers by the 1.409. And if I do that, I get 1 phosphorus. And my calculator, if I pull it out here, comes up with 2.50 oxygen. So again, we don't have a full-on whole number relationship here. We definitely have a fractional relationship with the oxygen in play here. So we've got to take care of that relationship. Now remember, the thing to do is we need to multiply both of these numbers by the fraction, the denominator of the fraction. We can think of oxygen as 2.5, which means I need to multiply both of those by 2. I get 2 phosphorus, and 2.5 times 2 would give me 5 oxygen. This would be an empirical formula of P2O5. So my first response here is P2O5 for the empirical formula. Now for the molecular formula, I need to use this molar mass, 284, and the empirical formula mass of P2O5 to figure out what it is that our multiplier is. Remember, our multiplier N is equal to the molar mass of the molecular formula divided by the molar mass of the empirical formula. And this is always going to be a whole number ratio. So up top, we know it's 284 grams per mole. What is the molar mass for P2O5? Well, I need to take 2 phosphoruses plus 5 oxygens. If I do that, 2 times 30.97 plus 5 times 16, I get 141.94 grams per mole. So that's what I'm going to put here, 141.94 grams per mole. My grams per mole cancel. 284 divided by 141.94 gives me almost exactly 2. So my multiplier is 2. That means that my molecular formula is equal to 2 times the empirical formula, which would be 2 times P2O5, which is P4O10. So P4O10 is my molecular formula. And so this concludes our review of Chapter 2, at least for these particular concepts that we found at the end of Chapter 2. If you have any questions, please feel free to reach out to me about it. But otherwise, have a good afternoon, and I'll see you next time in class.